Welcome the cool cat and dog on the awesome TensorFlow journey, even as we engage in this video where we use Microsoft's cat and dog dataset. Now downloaded, let us data clean. In cleaning our dataset, we'll have to remove the corrupted images. The libraries will be using the CV2, random, TQDM, glob, and OS. So we'll have to initialize the empty files list, after which we create a function that will verify whether the image is corrupted or not by trying to open it. If it's corrupted, it will return a false, else it will return a true. Then we'll now have to initialize a variable removed, for which if a corrupted image has been found, it's increased by 1. So and then we'll append the corrupted images to that list. And right now we're looping through the image paths and then running a verifying function. And then if it returns true, then we append to the files, else we'll have to append it to the corrupted list and remove it from the directory. And then we increase our removed by 1, and then we print all the corrupted images, and we also show the number of corrupted files that have been removed, after which we randomly shuffle the files and then print the length of the files to see how many clean images we remained with from our dataset. First of all, we are going to need the following libraries: TensorFlow, CV2, argumentations, and also transforms, and TQDM. Then we'll also initialize auto-tune. So after which we'll define the transforms that we need, that's normalize, cost dropout, haven't used cutout, and flip. And then we are going to create a class, and then we are going to initialize the init. Then we create the attributes that we need, and then after that we initialize the transforms in the compose to get all the transforms and put them together. So we are going to use the normalize. To normalize, we go to cost dropout, which puts random holes in the pictures. After that, then we go to the flip, and then we go to the test transforms, for which we only need the normalize. And then we are going to create read input. First of all, we decode the path, then we read it using CV2. We convert the color to RGB and resize the images. And then if it's training, we need both the images and labels, so we'll have to get the label, and then integer encode it, and then categorical encode it. And then after that, we return both the image and label, else we only need the image itself. And then we create the augmenting image function. That one will use the augmentations transforms to take the image, apply the transforms. After that, we return the image. But since we can't use it directly in a dataset object, we will have to wrap it inside another function with the use of a tf.i function to make use of it in the tf.data.dataset object. And then we specify the inputs, and then we specify the format of the output. And then after that, if it's training, we want both the image and the label, else we only want the image. Then we now create the load data function where we get the paths, convert it to a dataset object. If it's training, we want to map the data through the read inputs function with the input, and then we want to output since training is true, and then we have to auto-tune it to make use of multi-threading. And then after that, we again map the preprocessed data for augmentations of the images, and we also again make use of auto-tune. And then after that, we shuffle and we batch, and then we prefetch. If training is false, we'll only need one output. So in this case, the read inputs will have one output, and then again for the preprocessed data, we'll only have one output. After that, we'll shuffle, batch, and prefetch. Then after that, now we return the dataset that we need to the calling variable that is in the main file. In our main file, we can use the class that we defined for data loading in order to load the data. So we're going first of all to import the libraries, that's TensorFlow, NumPy, train, test, split, TQDM, progress, OS, and glob. After that, we import the class from our file, that's data loader. Then after that, we set the seed globally for libraries. And then after setting the seed, we also clear session, and then we set configurations for the seed, image size, labels, and batch size. Then we run the function in order to set the seed globally with set seed now 42. After that, we get the image paths we'll set recursive to true in order to go through the nested folders. Then we'll shuffle through the paths, and then after that we get the train and test paths. Using the train test split, the input is paths, 75% train size and 25% test size. And then after that we now create an instance of the class in order to get an object for our dataset. In this case, we want to create a dataset for our train images together with the batch that we want, the image size that we want, and we want the images and labels, hence training true. And then after that we therefore load the data using the load data method in the object, and then after that we can get to view the number of batches in the data using the cardinality method. We as well want to visualize the images and labels from our dataset object, so we are going to create the visualization class. So first of all we import our libraries, that's argumentations, matplotlib and numpy, and then we start to create our class. We start with the init function, and then we use the super constructor. We initialize the attribute labels, and then after that we want to inverse normalize our images, so we create an inverse norm method. We take the image, we multiply by standard deviation, we multiply by 255, and we add it to the mean, which will again be multiplied by 255, and then we return. We'll have to now create the visualize method, of which first of all we want to create an argumentation lambda in order to wrap the inverse normalization function, and then we set the probability to 1.0, and then if it's training we want to get the images and labels from batch. If it's not, we know that the labels are not there, so we use demi labels. After that now we want to get images of size 10 by 10, so we look through the images and labels as a pair using the zip, and then we use an enumerate to extract this index, and then we create a 4x4 figure. In the training we want to display the labels as titles, and then we set the axis off, and then we just normalize the images before finally rendering all the images in the figure. Using the visualization class in our main pipeline, we import the visualization. We then create an object from the class visualization. We take a single batch and visualize. Now that we are done with the process of data cleaning, data preprocessing, and data visualizations, we are going on to implementation of the architecture that we are going to use. So in this case we are going to use the MobileNet version 2. We are going to use the concept of transfer learning. We are going to use the input layer, the flattened layer, the global average pooling 2D, dropout and dense, and then now on to implementing our architecture. So we are going to instantiate the MobileNet version 2 architecture. We are going to use the ImageNet weights. After that we are going to freeze the weights in order to avoid those layers from being trained, and then after that we're going to now use the functional API. So we are going to start by defining the input layer with the image size that we want. After that we're going to use the base model, that's the MobileNet version 2. Then we're going to do global average pooling. For that we're going to flatten, and then we use dense layer with activation railing, and then after that drop out, another dense and another dropout, third dense followed by the output dense, which has now outputs 2, whether it's a cat or a dog. Of course we are not using any activation since we are going to use the logics. After that now we instantiate the model, pass in the inputs and the outputs, and then we view the model summary, and that's it. On to training the model we implemented. So first thing first, we're actually going to initialize the optimizer, that's the stochastic gradient descent, and the loss function, of course from logits true since we are using logits at the output of our model. And then we are going to initialize the train and val accuracy metric, and then after that we're going to use the time library to track the time between each epoch training. So we're going to use epochs 100, or rather any epoch you'd want to use, 10, 50, whatever. For every epoch we want to get the batch, we want to track the logits and the loss value, and then we want to propagate the loss value to the weights, and then after that we want to optimize the weights using the gradients, and then after that we update the state of the train accuracy metric, and then for every batch at the 500th step, we want to get the training loss and the step, and then after that we want to get the result of the training accuracy, and then we want to display it, and then we want to reset the states. Now that's after the epoch is complete. We want to get the training accuracy, and then we want to do a validation, for which we also do the same thing. That's pass the validation batch through the model, get the logics, then we get the accuracy of the model. Then after all that, we also print the validation. So essentially, this training data and validation data, you can do so by splitting the parts and then instantiating a dataset object on the train and validation data. We are in the inference pipeline, so we want to do inference in both TensorFlow and TensorFlowLite, and how to convert our model from TensorFlow to TensorFlow.js. So the libraries that we'll be needing are TensorFlow.js, Matplotlib, CV2, TensorFlow, and Globe. Then after that, we import the normalization and the rescaling layers. Now after that, we get to define our configurations. That's the image size, the seed, GPU. That's if you be using a GPU, should have been a list. And then after that, the labels. Then now we define our production model class. Of course, we start with the init, we get the super constructor, we define the attributes. Then after defining the attributes, including the softmax layer for probability densities, we get to the call, where we now define the flow of our model. Then after that, we get to import the model that we trained in the previous part. Then we implement the production model, and then we save it. Now that will be used in the Flask backend. Now we go to the read image pipeline. Then after that, of course, the last line, that's expand dimensions, has to expand dimension to introduce the batch dimension, which is essential during prediction of a single image. So we load our image paths, that the image is stored in the run folder, and we visualize the images as we predict them, of course with the predictions now in the title. And then after that, now we go to the TensorFlowLite. That's conversion from TensorFlow to TensorFlowLite. First of all, we go to the line, then we do a conversion, and then after that we save the model in TensorFlowLite format, and then we load the model. Now as interpreter, we allocate tensors, and then we get the input and output tensors, which is essential during prediction. Then now we again visualize the images as we read the images, set the tensors, invoke, which is used to run the prediction, and then we get the output of the prediction, and then we get it as a string, and then we show the image, set the prediction as title, and then set axis off, and then show all the images. Now going on to TensorFlow.js, what we discover is, since we create the production model as a subclassed API model, now we get an error. And what does the error tell us? Essentially, the error states that since we did not use this functional or sequential model, we cannot use this line to convert TensorFlow to TensorFlow.js. So instead, what I did, first of all, save the model as in the recommended format, after which I used a command line code, this one, to essentially convert it from now a TensorFlow saved model with the folder given there to a TensorFlow.js model. So you can try to do the same, but with the functional model or the sequential model. It's possible both ways because the model has a linear topology and there are no branches, so it can be implemented as both functional and sequential model. So instead, you can do the same and then try to use the particular code to convert it from TensorFlow to TensorFlow.js. Let's work on the backend, the Flask backend. So we import the libraries, then we instantiate the app object, model none, then we create the function to load the model. After that, we implement the configurations that we want in the class, and then after that we create the function which will load the images as required, convert it to RGB, and then resize it, and then convert it to a NumPy array, and then expand the dimensions. After that, return the image. Then we create a route predict, which is post. We'll get the image, and then we'll preprocess it with the required size. Then after that, we'll do the predictions, and then get the prediction as a string and assign it to a key in the data dictionary. And then after that, we set the success to true, and then we return the data as a JSON. And then if this is the main thread of execution, we'll have to print the line, load the model, and then start the Flask app. Now onto the command line to start our app. So after writing that command, the app is now starting. As now the app is started, it's running on port 5000. So let's go over to Postman and send a picture to the server and receive the response. So over at Postman, we are using localhost port 5000. The route is predict, and then we go here over to form data. First of all, we choose file, then the key is image, and the value is now our picture. Let's start with the dog picture here, and we send it. We get prediction of a dog. Now choosing a cat image, sending it, I get prediction is a cat. Let's also use curl to send our picture to the server and get a response. So we are in the images folder, that's the run folder. So using curl, we want to do a post, and the file that we want to use is an image. Let's choose the second image of the cat, and then we want to send it to the localhost port 5000 and predict. Yes, so we get the response using the curl to send a picture to the backend and receive the response. So we are on to running the TensorFlow JS model on a Node backend. So of course we first create the package.json using the npm init command, after which we add a line of code here to use import and require in the file. Then we import the libraries we need, that TensorFlow JS for the browser, and then we also define require. Then we require globe for getting image paths, gim for reading the image and resizing, and we also define the data folder and the model URL, and now we load the model. Then now we get the image paths, and then after that now we define the brains of our code. Now we get, first of all, get the image paths, then we introduce a try. So for each image path we'll have to first read the image, then resize it, then convert it to a tensor, then introduce the batch dimension, then we go to the prediction. So we go to predict, and then we log the predicted output, else now we log the error. Then now we get our main part of the code to go into action by using await image loader. In our TensorFlow JS model folder, we can start the HTTP server. So after starting the server, now we go over and run the Inference.js file. Again, we are onto TensorFlow JS model, but now this time instead of using a Node backend, we are using an Express backend. That's the implementation of RESTful APIs. So let's again import the libraries that we need, then define require, then after that we import Express, then we instantiate an app, then we define port, then we require file upload to get the files from the front end, then we use gim for image reading. Now on to FireBase. Let's start by creating a project. Let's disable Google Analytics. After a project is ready, let's go to continue. Now we go to web and register app. Then we install FireBase using npm, and then this is the code that is going to be in our FireBase init.js. After that, go to FireBase Storage, get started, go to test mode, select default location. Now that we are in storage, we'll upload the files. So here we copy all the files for the model and upload them, and that's it. Since I've pushed the model over to FireBase Storage, I'll now load the model from FireBase Storage. So first thing, we create a reference to the FireBase Storage, and then we load the model, and then after that we log the model loaded. So now we call into action the model loading. So let's go into the core of our model. We read that data using Gym, we resize it, and then after resizing we convert it to tensors. Then we introduce batch dimension, do the prediction, then after that we convert success to true if prediction has been done, and then we return prediction. Now onto the route which gets the image data from frontend, passes it into the image loader, and then returns the prediction, and then we get to append the prediction onto the dictionary and then return it back to the front end. Now we go into starting our app. So the Express app is live. We'll be listening for any requests, then it does the predictions and send it back. This has been Everything Deep Learning. Thank you for watching.